Okay, so good afternoon, everyone. My name is Federico Pasquini. I'm with N.E.T, a company based in Milan, active in designing and manufacturing gas sensing solutions. We are an exhibitor here at Sensor and Test. We have been for a good part of 20 years. And today we're going to present you our latest innovation in gas sensing technology. It is a thermal conductivity based sensor aimed for the detection of hydrogen. Then over the future, the project aims at detecting other gases. As we will see, thermal conductivity is a technology that enables us to detect several gases, virtually any gas, to be honest. But for the time being, we're going to target hydrogen as the main target gas. And why? Because you all know that there will be a significant drive to enhance the use of hydrogen in several economical sectors over the course of the upcoming 10 to 20 years. Here's a brief agenda of what we will cover today. So we'll briefly discuss how the hydrogen economy is upon us and how it's going to impact us and how it's going to impact economical sectors. That's not, of course, the topic of this lecture, but we're going to give it a little context there. We are going to talk about the main application and detecting scenarios for a sensor for hydrogen. Then we're going to review what's available right now in the market for the detection of hydrogen, what technologies are there. Some of these we use, we implement, we manufacture, and we're going through what shortcomings they may have and how our new thermal conductivity sensor is going to overpass that. And then we're going to take a closer look at how we have implemented thermal conductivity technology into our new platform called MAC, M-A-C, which stands for MEMS analog catharometer. Catharometer is another word for a thermal conductivity sensor. So as we mentioned, over the course of the upcoming 20 to 30 years, there will be a significant drive to increase the use of hydrogen in several economical sectors. In order to decarbonize those sectors, free them from traditional fossil fuels, which have high impact on the environment. On the other hand, hydrogen, despite being just as energetic as fossil fuel, is extremely environmental friendly. It can be created from water using renewable sources, such as wind or solar power. There are other, of course, techniques to synthesize hydrogen. Those will be less, let's say, environmental friendly, but nonetheless, then the use of hydrogen will be friendly in the sense that when it burns, of course, it produces only water vapor. Typical detection scenarios when it comes to hydrogen, some of these are related to the use of hydrogen as a fuel. Some of these are related to the production of hydrogen from other scenarios, such as the use of lithium batteries. So the use of hydrogen into heavy industry, when hydrogen is going to be used as a source of energy, then of course there will be the risk of a hydrogen leak. And as we will see in the next slide, hydrogen is quite risky in terms of the ability to be flammable at even low concentrations. So there will be a high need to detect hydrogen leaks wherever hydrogen is used in industrial settings. We mentioned leak of lithium batteries. Hydrogen is one of the first gases that is released by lithium battery when a leak starts to occur and there's a risk of the so-called thermal runaway. So when a battery starts to increase its temperature up to a point where it becomes unstoppable and then a combustion is occurring. And therefore, hydrogen detection is used often as early warning sign of lithium battery leaks. There are several technical challenges to be overcome, but the intention is to use hydrogen as a substitute of natural gas in grids. And so all across those grids, there will be a need to detect hydrogen for safety reasons. Last but not least, fuel cells. Fuel cells are devices which are able to use the energy potential of fuels, of combustible gas, but without making an actual combustion occur, which is more environmental friendly. Fuel cell will be used with traditional gases such as methane or natural gas, but also will be more and more used with hydrogen, and that will be used also on vehicles. So that is a quite large future application scenario. So far, so good. But of course, we mentioned hydrogen being the one of the most flammable gases known to man. It becomes flammable from concentration starting at 4%. That's so-called lower flammable limit of hydrogen, LFL, all the way up to 74%, which is the upper flammable limit. So any concentration between those boundaries, in case of an ignition source, can cause flame, and in case of confinement of the gas, even explosions, of course. On the other hand, it would be hard to detect a leak without proper and reliable detection technology, because hydrogen is colorless, odorless, and tasteless. So there's no risk of somebody identifying a potential leak just because of odor or seeing the gas. That's pretty invisible to all human senses. And therefore, availability of reliable and selective gas detection technologies seems vital for a safe transition into a true hydrogen economy. Hydrogen has been detected for the good part of 40 years with two common detection technologies available here in the marketplace. Again, we use those technologies, we manufacture those technologies, we are well aware of what's good and bad of these, what limitation those technologies have. We wanted something able to overpass some of those limitations. First of all, electrochemical cells. Detection range has been expanded today all the way up to the flammable limit of 40,000 ppm or 4% volume. In the past, it was relegated more to low ppm detection, but today there are several solutions, including from us, that go all the way up to the flammable limit. Main concern, main knock on electrochemical cells, the intrinsic drift of that technology. Typically about 2% per month. So the cell, by being exposed to target gas, interfering gas, or even the environment, has a natural drift due to degradation of the internal electrolyte. Therefore, typical operating life, 24 months, that's the approximate span of time required for the initial sensitivity level to fall below 50% of the initial value. Of course, it has cross-sensitivity to other gases, so electrochemical cell may react to other gases other than the target. it has to be replaced potentially after very high exposure. So a very high exposure to the target gas may quickly deplete the electrochemical cell to the point that it needs to be immediately replaced even before the 24 months, which is the nominal operating life. Plus, can only operate in presence of oxygen. So the electrochemical reaction which occurs inside the cell require oxygen to occur. So it cannot be used in scenarios where there's pure oxygen, for example, because the presence of oxygen is strictly required. The other typical technologies used so far for hydrogen detection is the catalytic bead sensor, or they're at times called also pelistors. They've been on the market forever. They've been a very cost-effective solution to detect flammable gases. They're quite linear all the way up to the flammable range, typically, up to about 4%. Well, typically up to 60% LEL, sorry. Their detection range is up all the way up to 100%, but then beyond 60%, they tend to be less linear. But of course, normally, cat bead is used to activate alarms at lower percentage of the flammable range, for example, 25%, 30%, maybe 50%. It has its own drift, so maybe it is more stable than an electrochemical cell, but over time it may tend to drift. And that's the typical drift data on the sensor we implement in our range. Reacts to any flammable gas. Well, yeah, the cat beads not only react to hydrogen, but any flammable gas make the sensor to react. There are ways to filter, there are ways to power the sensor at different voltage level, which may make the sensor more sensitive to one gas or the other, but in any case, it will react to any flammable gas, including methane, hydrocarbons, ammonia, even other gas which we may not think as flammable, such as carbon monoxide. They tend to react with cat beads. And again, just as an electrochemical cell, it may have to be replaced after high exposure, as the sensitivity level may not recover from very high exposure to the target gas. Another common knock is catalytic sensors are susceptible to contamination and poisoning. Certain chemicals may cause the sensor to enter a state where they become unresponsive to the target gas. Typically, silicon matters tend to basically form on the catalytic surface and inhibit the correct reaction on the sensor, and therefore the sensor becomes unresponsive to the gas. And just as electrochemical cells can only operate in presence of oxygen, because basically a catalytic sensor will function with a small combustion on the surface of the catalyst, and therefore it requires oxygen to occur. Again, those technologies with their good and bad, with their pros and cons, have been used in the industry forever by knowing their limitation and by knowing what's the best application scenarios for it. But we wanted to overcome those. And we started to consider thermal conductivity sensors. Thermal conductivity sensors are nothing new in their own right. They've been in the market forever. Basically, a thermal conductivity sensor is common technology enable us to determine the concentration of flammable gas, but we can go above the so-called lower flammable limit. We can go all the way up, theoretically, to 100% volume. Traditionally, producing thermal conductivity sensor was quite an issue for the high power requirements of the sensor itself, and the difficulty of producing with great repeatability the circuit and the sensing element required. All that tended to translate into high cost of ownership for the users. But nowadays, by using common CMOS MEMS technologies available in the market for many other applications, is significantly lowering those production costs, is significantly reducing the power consumption required to operate the circuit, and is improving repeatability of the process. Therefore, nowadays, thermal conductivity sensing elements are available with a far greater cost of ownership for the users. How those thermal conductivity sensor works? Basically, we have two beads, two resistors. One exposed to the target gas, it's called the active bead. One sealed in a glass with a reference gas, which is typically air. So basically, we're always referring the active reading to the reference reading of a sensor sealed in air. If the circuit you're seeing here sounds familiar, because that's pretty much the same circuit, a Wheatstone bridge used in catalytic sensors. They also have a reference and an active bead. They also confront the values of two resistors, one exposed to the gas, one used as a reference. In this case, though, we measure the difference in the thermal exchange on the active bead, the one exposed to the gas, that one is able to exchange heat with the gas, against the reference, which is sealed in air. So it always gives us the reference thermal exchange with the resistor and air. Of course, any gas can cause a little reaction on the reference sensor. Any gas basically can have a thermal exchange with the active bead. But the more different is the thermal conductivity property of the target gas to the one of air, and the greater is your signal. And the lighter or the heavier is the gas as opposed to air, and the more it will exchange heat with the resistor. And therefore, thermal conductivity sensors are particularly suited to measure the concentration of gas, which are either much lighter or much heavier than air, and such as hydrogen. Hydrogen is the lightest gas there is. Other very light gas, such as helium, can be effectively detected with thermal conductivity. And on the other hand, it can be used for heavy hydrocarbons as well, but that's not the aim of our project so far. So we implemented all that to design a sensor that was able to go from ppm level all the way up to 100% volume hydrogen detection, overpassing the typical limit of 4% volume of catalytic sensors and electrochemical cells. Our sensor has an extremely high long-term reliability, as there's no chemical reaction, there's no contamination on the sensing element. The intrinsic drift of the sensor is very low. It only depends on the thermal exchange, and then there's nothing else happening with the sensing element. That it makes it reliable also in harsh environments. It has a very fast response time because the thermal exchange happen very, very quickly once the sensor is exposed to the target gas. Therefore, we expect a response time within a few seconds. Very high resolution. That depends on the technology we use on the sensor, but we aim at 2 ppm of hydrogen. Very long expected lifetime, again. There's no chemical reaction, there's no resonating parts, there's no lamp emitting lights, nothing that can really degrade over time and cause a drift. And therefore, we expect a lifetime all the way up to 15 years for such sensors. We have designed an internal cavity inside the sensor because the thermal exchange is, of course, highly impacted by convection, and therefore we have designed a cavity which causes the gas to stabilize and minimize convection on the sensor, which can impact the thermal exchange and therefore the signal. Can operate without the presence of oxygen. The detection technology does not depend by any means by the presence of oxygen. It uses proven technology used in other sensor manufacturing processes as a very low working temperature. The active resistor only operates at about 2 degrees above ambient temperature. This gives us two advantages. On one hand, very low power consumption. The sensor can reach the intrinsically safe approval. But on the other hand, by working above the ambient temperature, we avoid any condensation of the sensor, which of course could impact the reading. The MEMS technology we use offer great resistance to mechanical shocks, so it is a technology that can be used also in portable application where robustness is of the essence. We are going to apply an active environmental compensation. Thermal conductivity sensors are impacted by changes in relative humidity, temperature, and pressure. All that affect thermal exchanges, and therefore you need to compensate for that. We are going to install a temperature, relative humidity, and pressure sensor on our sensing element, and therefore we'll be able to always actively compensate against environmental changes, thus having a very reliable measurement at all times. We're going to implement the sensor in a standard industrial size and footprint, the one that has been used for the good part of 30 years for NDIR sensors. All right. Conclusions, as time is almost running out. Thermal conductivity has been a promising technology for the detection of hydrogen for years, but now with the implementation of MEMS technology, we're able to lower the total cost of ownership and make it very effective in very different conditions, including hard conditions. The detection technology is very safe and stable. Again, no reaction, no chemical or physical reaction, no optic or lamps, which can maybe drift over time, no resonating or moving part, which can degrade over time, and therefore very high expected lifetime. Very low power consumption, good for either fixed or portable application, shoot for intrinsically safe approvals. On the other hand, there's a need for a strong environmental compensation and effective calibration in order to enhance the signal against the environmental noise. One last consideration not included here, which derives from some considerations we made over the course of the lecture. Not a good fit if there's a simultaneous presence of different gas in the environment, because as we mentioned, thermal conductivity sensor react to any gas, some more, some less, but it reacts to any gas. Therefore, if you're operating in an environment where you may have different gas present, then it's probably not a good fit despite our best effort to enhance the hydrogen signal against anything else. If you have further questions, I'll be here, and we have a booth, again, 104. These are my contacts. I also brought some business cards, and in case somebody is interested, I also have some documentation on the sensor. Thank you very much for your attention. I'm willing to take any question you may have. We still have a few minutes. Thank you very much indeed. Again, we are it will handle changes of humidity because we are going to have a relative humidity sensing device inside the sensor. So we're going to measure relative humidity, and we're going to compensate for that. During our development, we are doing studies in our environmental chambers against several combination of temperature, relative humidity, and pressure against a known concentration of gas. And therefore, we are deriving all the calibration curves which are going to be actively implemented inside the sensor. Again, we aim for 2 ppm of hydrogen. Sorry? No. 2 ppm. So we're able to discriminate between concentration differing the one from the other from 2 ppm. So if there's a difference of 1 ppm, that gets kind of lost. But if we go into percentage, then of course no problem. 2 ppm is 1/1000th of a percentage. Yeah.